Hello everyone, thanks for taking the time to join us today. We're just about to start on our latest webinar on IP software. I'm Ross Brackenridge, I'm the Technical Manager of IP. You may remember the previous webinar we had was an overview of all the additional modules that you can add on to the base license of IP. So that was a summary of all the advanced modules. Today we're going to take a more focused look at a particular group of advanced modules that by using them together we can get quite a powerful workflow for improving the characterization of your reservoir. Today's presenter is going to be Paul Spooner, who's our IP product champion. There will be a recording provided of the webinar afterwards. Now, unfortunately, due to the logistics of presenting this in 3 different time zones, we won't be doing live Q&A after the presentation, but we will respond to questions very soon after the webinar. If you do have a question, you've got a couple of options. You could use the GoToWebinar panel. You'll see a drop down that says questions. You can type in a question there and we will respond to that after the webinar. Or alternatively, and this will be your only option if you're watching a recording of this, is to contact us through our digitalproducts@lr.org email address. Some of you will be IP users that may already have these advanced modules. If you don't, and you would like to try using some of the modules you're about to see in the presentation, then please contact us on the same email address and we can arrange to get some evaluation licenses to you. Okay, with that I will hand over to Paul. So enjoy the webinar. Thank you.
Hello and welcome to our latest IP webinar. I'm Paul Spooner, the IP Product Champion, and today I want to talk to you about a few more of the advanced workflows and how they can be integrated for more effective use when it comes to static and dynamic modeling and the whole sort of reservoir characterization workflow. The typical inputs to a static model, a geologic model, would be, the results of my normal volumetric interpretation, which might be deterministic, non-deterministic. So things like porosity, V clay, V shale, mineralogy, facies, those sorts of inputs. And the primary input to the dynamic model is the saturation height functions, because that's the primary way in which we, within the model, we model a fluid distribution. The distribution of water saturation across the reservoir is height based above free water level. Now, how you do that, how you do the saturation height modeling, does have significant impact on the results of the dynamic modeling. Normally, I would not expect that you do an interpretation, you build a saturation height model, you give it to the reservoir engineer, and everything just works and everything is perfect. No, usually there needs to be some iteration, some going around, trying a variety of different things, seeing what fits, what doesn't fit, coming back and adjusting it, and that's some of what we'll look at and the sorts of tools that you can use to improve the results here. And in particular, this is around looking at the hydraulic flow units and then predicting those flow units in the reservoirs using something like 3D-SOM or cluster analysis. This slide here kind of, I've got it in here to kind of, try and explain, why this is fundamentally important. So in any particular reservoir interval, I might be fitting J functions, for example. Now, I could take one reservoir interval, and because a J function, being a poor perm function, it does capture a range of porosities and permeabilities in the rock, and I could take one whole reservoir interval and then fit one J function, and I'll get a reasonable result. But if I actually have 3 rock types distributed in the reservoir here, and I've just called them here A, B, and C, and rock type A is a better quality rock. B not so good, C quite poor. Now, in reality here, rock type C might be quite lower porosity, lower permeability, maybe silty, quite shaly. A lot of people might already have actually taken that out of the reservoir, and it doesn't even figure as part of the net because they've applied some sort of cut-offs, and they've been a little bit overzealous in doing that. And it's important to understand here that rock type C actually is a reservoir quality rock. It just needs to be high enough above the free water level to be able to store the hydrocarbons. And now what a lot of people get really focused on when they're doing saturation height modeling is paying attention to the fitting of the functions, making sure that you get the right characteristics for rock type A, the right PC curve, height function for rock type B and C and so on. And they kind of lose sight of the fact that actually, it's at least as important, and quite possibly more important, to actually make sure that you get the right characterization in the reservoir, the right sequence, that you recognize where is rock type A in the reservoir, where is rock type B and rock type C, and how much of A do we have and B and C. Because I might have got perfect functions for rock types A, B and C, but if I don't get the distribution, that left-hand column, if I don't put those in the right places in the reservoir, then my saturation that comes out, the right-hand curve, that is not going to fit at all and is going to have quite a lot of error. So if I, miscategorize rock types A and B, for example, and don't recognize rock type C in the reservoir, or I don't see enough of it, then I'm going to severely impact on the productivity of that well. So it is at least as important, if not more important, to get that ABC characterization in the rock type column as it is to get the right shape for the PC curve for those rock functions. Now, this kind of characterization of the rock type, in the industry we often talk about facies, and it's very much a geological term, and that tends to be the input into the static model. But reservoir engineers tend more to talk about flow unit or rock type, because what they're really interested in is the storage capacity and the flow capacity, so the porosity and the permeability. Now that's why we have rock typing modules. At the end of the day, the mathematical processes don't know the difference between geology, reservoir engineering, facies, reservoir engineers. It's up to you, the interpreter, to use the tool accordingly. But the one module that we do have that is very specific is the hydraulic flow unit module, because that is designed to recognize flow units. Now, so the primary task of the job here is that once we get into the saturation high functions module, yes, we're going to be fitting functions, shapes, curves here to the PC data, for example with the J function, but we need to fit them to each rock type A, B and C, because now we could just fit one to the whole reservoir, but we'll get a better result if we can actually characterize the reservoir and split them out independently and get separate functions for each rock type A, B and C. Now, at this point as well, it is also worth pointing in mind, don't lose sight of the fact that where possible, we're going to be trying to fit functions to core-derived PC data. But we don't core all the reservoir, so we may well have missed some important rock types, and we may not even have cored rock type A. So if there's a section that we see in the logs of higher porosity, higher permeability, it's really important to characterize that. So we might have to do log-derived functions, but of course we can do that inside the saturation height module as well. So let's take a look at an example of this then. Here's a fairly simple shaly sand well. I've got over 400 conventional core Paul Perm data here, for which I've just done a simple single regression and applied that in a user formula to calculate permeability, and that's being shown in here. It's reasonable permeability, although there's no discrimination in here. It's just one single function across the whole reservoir interval. So let's go ahead and try and use this in a saturation height module. So there's PC data in this as well, much less PC data, which is a very common scenario. So I've picked up those PC data along with the porosity permeability for those plugs, and it's centrifuge data converted to reservoir conditions, so applying the stress correction and doing the fluid substitution, so mapping in the contact angle interfacial tension for the reservoir fluids and also the right fluid densities at reservoir conditions. This is where you can see the 8 plugs that we have. One of them I've already switched off because it's actually not very good data. So I've only got 7 plugs that I'm working with. So I really am kind of limited as to just how much I can do with this. If we actually just take a quick look at the the corrected data, so this is at reservoir conditions, and just using the porosity here as the z-axis, you can see that, that is the lowest porosity plug. And that is the highest porosity plug. So whilst there's a bit of a trend in there, yeah, they are slightly mixed up. So, not perfect or ideal data, but let's see what we can do with it. So when it comes to fitting the functions, there's a whole range of functions that we can apply in IP. And actually, for that matter, there's also 3 completely separate workflows here as to how you work. But if I was picking based purely on the R squared, then an initial look at the data would suggest maybe this function is the best one, but I'm going to use this one just because, let's just say, the reservoir engineer demands that I use a Leverett J function, and the lambda has got the best R squared of those. So now, never just pick a function based purely on its R squared. Always, take a look at the results. Now you can look at how the J function actually fits the data. So looking at all the plugs in here, it's one average function going through the data. There's a bit of a hint though that there's more than one rock class in there maybe. That's slightly more apparent if we actually look at it in a linear plot. You can kind of see that whilst that's one average function, there's at least 2, maybe even 3 functions splitting out in here. So let's go ahead and apply that one function anyway and just see what it gives us in the reservoir. So going into the saturation versus height curves module, of course this function is going to be applied as a function of TVD. So we're going to bring in a TVD curve, porosity permeability. This is a perm that I derived from the core data, my log derived SW. The mixing in here, it's just a one-to-one mapping to the J function that I created. And then in the well, select the depth intervals, fluid densities, free water level, which might have just come from an interpretation of the logs, or it might be from pressure gradient, or whatever else. If I then take a look at the results in the well, let's just zoom in a little bit here. So not perfect. It's a pretty reasonable trend, but SW is definitely a little higher at the top than I was calculating from the log. Now, some of that might be some uncertainty over the interfacial tension at reservoir conditions, and I could use a regression tool to try and optimize that, for example. Which now that's about the best I'm going to get without doing any more. So now let's go back and have a look and see if we were to actually apply some rock classification up front, could we actually get a better result? The simplest way of doing the classification is just manually, directly from the PC data itself. You can pick and populate this rock class value. You could just type numbers in here. You can just go in here and manually type numbers in. But to do it interactively, any of these QC plots can use the z-axis, the color for the z-axis, to be the rock class. Because I don't currently have a rock class value in here, it has to populate it with a number. So do you want to start with a 0? So if I say yes to that, then all the plugs are being plotted in here. Let me just change scales a little bit so it's easier to see. And then I can right click and set the rock class. So I might decide that I think the poorest quality rock is this one in here. Then I might decide this one's rock class 2, and so on. You can you could set these through here. You just have to get the cursor right over it. Now this works on all of the plots. All of the QC plots can be used for this. So having picked one set of rock classification there, so you can see it's been populated, I could use all of these. So the pore radius, pore volume plots. You could look at how they split out across there. Decide how you want to split them out. Likewise, the apex plot. So it can be, this rock classification can be done on all of these plots. It can also be done on the J function plot as well, because if you actually pull up the J function plot with the z-axis being the rock class, you can also set the rock class in here as well. Manually assigning the rock class, via these plots, that's fine if you've got tens of plugs, but if you've got hundreds or thousands, then you're not going to want to do that manually. You're going to want to use some sort of auto classification technique, and that's going to rely on using some of the other advanced modules, either the rock typing modules, say cluster analysis or self-organizing maps, or maybe one of the curve prediction modules, say like fuzzy logic or neural networks. All of those could be used to do the rock classification. And there's a variety of data that you could use as input for that. And one very useful feature is to use the PC functions. If you use the workflow that is a separate equation for each PC curve, then you can pick any one of these types of functions in here, for example, and when you do the regression, you get unique coefficients for every plug. And those coefficients can be output as curves. So along with those coefficients and the plug porosity and permeability, you've got 5 curves there, which can act as the inputs to the classification methods, and that can work really quite well. Alternatively, another method is to use... Actually, I'll stop there. Another excellent method is to use the hydraulic flow units module. Now this is using porosity and permeability data, typically my core data, conventional core data. If I have enough scale data, then I could be using the porosity permeability from that. It's a multi-well module, so of course I could be bringing in core data from across an entire field to help get the characterization. And also very often you maybe don't actually have core in all of the rock types, so you can use log-derived porosity and permeability, and that's great if you've got something like an NMR log, because then you've got an independent measurement of permeability. Maybe if you don't, getting that permeability can be problematic, because then if you just do something like the single regression function like I showed at the beginning, then maybe the permeability might be the restricting factor in the quality of the results. You can apply discriminators, by reservoir unit, by zone, whatever, take out the bad hole, things like that. When it comes to the actual flow unit methodologies, there's 4 workflows in here. Lucia, rock fabric number, is a carbonate workflow, so I'm not going to do that here. And for clastics, we have 3 workflows, RQI, there's the relationships there, Winland, Pitman. These are all just different poor-perm relationships, but the interactivity and the methodology is the same between all of these methods. Within IP, within the module, there's a default 5 flow units that it searches for, and it will seed the module using cluster analysis. But because I've already looked at the PC data and decided that I want 4 classes, so I'm saying that I want 4 flow units. If you go ahead and then make the RQI curves, and then pull up the interactive FZI plot and the Lorentz plot, this enables you to interactively adjust those boundaries. Now, you could just adjust those boundaries looking purely in terms of the data. So if you decide that you think that's a better classification here, you can see how that's changing. The two are interactive together. If you apply those and write out the HFU curves, you can then look at the results on a poor-perm crossplot and see how your classification is then being applied to the poor-perm data, as well as seeing the poor-perm relationships for each of those flow units. So, for example, you can see the impact of, if I was to pick this peak instead, now if I look at this, I've got one trend of data in here that's being split by 2 different flow units. So I've decided that I want to pick my boundary here so that sits out as being uniquely in part of flow unit 4. That's the sort of things that you can do. Now, once you've decided that you're happy with those classifications, you can output, because for each one of these flow units there is a poor-perm relationship, and you can either output those as a text file or as a multi-line formula. If you save it out as a multi-line formula, you can then open it and run it and edit it. You could save it and run it on all the wells in a field. The only things I've had to edit in here is that, so there's the Paul-Perm relationship for each flow unit. It's a porosity function. So I've put in my log-derived porosity in here, and it's a function of the flow unit. So what I need to do is I need to come up with a way now of extending this core flow unit module. Each core plug, I've determined a flow unit for it, but I now need to extend this model, this core model. I need to extend it to the wells, and I'm going to do that. And I've already been in here before, and you can see that because I've done it using SOM, but it could be done using any of the curve prediction modules. So what I want to try and do is use some log inputs maybe to predict the core flow unit in all the wells in all the zones of interest. And then if you input that result into the multi-line formula, you'll be able to calculate permeability through every well as a function of porosity. So having determined the HFU for each core plug, we can come in and bring that in now into the PC setup module. So then when we look at the plugs, the HFU is now populated, and rather than my manual classification, I can just go ahead and use copy across the HFU, so that I'm using the HFU for the rock classification. Of course, at that stage I can manually edit if I so decide. If we have a quick look at how those functions split out, not functions, but how the rock class splits out across the plugs. So bearing in mind these came from the HFU module, that's they look like split out quite nicely. Then we can go ahead and fit functions unique for each one of those four rock types. So all I'm going to do is continue to build a J function, but the only difference is that I'm applying a discriminator now. So I'm using the rock class as the discriminator. And I can go ahead and do this for 2, 3, 4 functions. If we look at the actual functions, so if we compare the, so there's the J function for rock class 4. If we then go to rock class 3, for example, and look at the outputs for this one. So again, that's 2 plugs, but 2 different plugs. So we're getting a much better fit now to the plug data because we've split them out by rock class. Now, to be able to apply these functions in the wells, there's still 2 things we need to do here. First of all, we have to extend the hydraulic flow unit module to the field, to the wells, because that was derived from the core conventional Paul-Perm data. So that HFU number only exists where we have core data. So we need to use some sort of predictive model. Now, whether that's from the rock typing module or the curve prediction module, something like SOM, cluster analysis, physiologic neural networks, DTA, whatever. But we need to build a predictive model based on the log responses to be able to extend that model. And then when we come to applying the functions as well, and I've just derived J functions, which are porosity permeability functions, so I need permeability in the well. Now, I've already created a permeability. That was just from my straight, one simple Paul-Perm function. But, as we saw when we were looking at the HFU module, we could probably do better because we can get, now we've got a characterization, a Paul-Perm relationship for each of those flow units. So we could use the HFU permeability equations and use those to calculate permeability. So again, for that, I need to know the HFU at every depth and every well. So let's do this. We'll do both of those steps, using the SOM model to distribute it, and then using the HFU relationships to get the permeability from that. Now, the first thing I'm going to say here is that you'll notice I'm going to show you the SOM in just a second, but the inputs, I'm working from the raw logs here, but I am actually I precondition the logs, if you will, by instead of using density neutron and sonic, I'm using the hydrocarbon corrected curves, which are there are optional curves available in FSW. So when you do your deterministic interpretation, the raw rho B log, of course, is going to be affected by gas, oil, water. So the hydrocarbon corrected one takes it back to a true liquid-filled porosity, if you will. So alternatively, you could have just have used, say, porosity, V clay, and things like that. But if you're using the log inputs, I would recommend that you use hydrocarbon-corrected log inputs. This is the SOM module. It's a multi-well module so that I can predict the HFU across all the wells in the field, although I'm only running it single well here. My input, log curves, hydrocarbon corrected, and the core derived HFU that I want to predict effectively. I could be running this zonally because I can pick specific zones to run it over, but I'm just running it over the whole well. Similarly, I could apply discriminators, take out bad hole, etc., but I'm just running it over the whole thing. The training takes quite a few seconds to run, so I've already run that, and this is the trained map. So the data has been sorted by the Cohenum self-organizing map algorithm, but at the moment I've got 642 nodes, but I have not yet calibrated those nodes, so I'm going to calibrate to the input curve, to the HFU, which of course has 4 values. So this is now the calibrated map, where every node on this map has been mapped to a facies, a rock type, based on probability. And you can manually reassign these if you're not, if you've had a look at the logs and seen where the data actually sits, you can manually reassign them if you want to. I'm just going to run it as as it saw fit. When you run the model, so that's now calculated HFU in all the depths in all the wells. If I pull up a contingency table, so this is now giving me a comparison of where the core data actually exists. So for example, HFU 4, there were 184 incidences in the core, and I predicted 189. I was right 139 times, and you can look at that in terms of percentages or points, so you can see statistically how well you did. For me, though, it's much more important to actually plot it and have a look. So here on a log plot, for example, I can see where the incidences of the individual core facies are, and then so the solid shading is the predicted model, and these are the probabilities. This is where it's quite confident that it was hydraulic flow unit 4, and the second most likely was 3, and there's only a couple of instances of where it really was 3 in there. Now these things are all interactive, so I could, if I wanted, start investigating where those were, seeing which nodes they were on, because I might want to start reassigning some specific nodes. It's kind of standard cross-plot, log-plot interactivity. You'll see the cursor lighting up. I'm just going to use what I have here for now and see how that works. Now, we could have used a variety of other methods, not just SOM. And for example, cluster analysis, fuzzy logic, neural network, and they're all going to give slightly different answers, and they all have different percentages correct when you pull up the contingency table and compare them. So based purely on that, that might lead you to think that 3D SOM is the best model because it's got the highest percentage correct. But these numbers are they're a bit like an R squared. The best statistical match is not necessarily the best model. It really depends, and that's where you just have to look at the data, look at the plot, and really examine where is the model right and where is it wrong, because the significance of that is in our case HFU 4 is the highest porosity, highest permeability, so it's the most important flow unit, and if we significantly underpredict that, then the model is going to underpredict inflow. There's rules of thumb in the industry, like 10% of the rock produces 90% of the production. So you really need to get that 10% of the model right. And if you've got, say, a net to gross of 50% across the whole interval, and if the model was very good at predicting the non-reservoir, but in the reservoir intervals consistently got the wrong HFU, well, that's not so good. So it really does depend, and you just have to look at the data. No statistics can really kind of capture that. So now we want to come back to the saturation height model and bring all of this together. Firstly, we're going to use not just the single permeability, but the perm that we derive from the multi-line formula derived from the HFU. And now that we've got multiple J functions, we can create a new mixing, and because all of the functions that you have fitted are available here in a drop down. So I'm going to use HFU1, but if my SOM derived HFU, so this is at every depth and every well now, is 2, then I'm going to use function 2, and so on. If it's 3, I'm going to use function 3, and if it's 4, I'm going to use function 4. Now if we go back to the actual hydrocarbon model and then select the rock class mixing, and go ahead and run using this, ta-da, you can see a better fit here at the top. And if I now actually you can see now that my interfacial tension correction is now almost 1. There's no correction required because we've got a pretty good fit. Really, because we have now discriminated the reservoir into separate rock types. So the workflow that we've been through then was to use the hydraulic flow units module on a conventional corpore perm data to determine HFU. We generated functions, J functions, for each flow unit. We developed a predictive model to be able to extend that HFU model to the wells. We used the multi-line formula from the flow units to get permeability in all the wells at every depth. And then we used that HFU as the discriminator when applying the J functions in the wells. Now that's what you might consider to say be the recommended or standard workflow. But like anything, there's more than one way to do it. You could actually kind of turn this whole process on its head and do it in a slightly different way around. You could have started by using a predictive model. Now again here, this could be neural networks, neural network or SOM or any of those other methods to actually predict permeability from the logs at every depth, and use that permeability with your log-derived porosity in the hydraulic flow unit. So you determine the flow units directly in the wells from the log data, and then use that to discriminate for generating the J functions, and apply that as a discriminator when applying in the wells. Now, on the face of it, that seems like one step less. But either way, in both cases, some prediction is required. Now, whether that's for the HFU, predicting that in the wells, or for the permeability. And there's pros and cons to both of these. Some people consider that predicting HFU in a well is a right or wrong exercise, because if it's flow unit 4 and you predict 3, well, that's wrong. But if you predict permeability, and if the answer is 27 millidarcies and you predict 30, well, that's only a little bit wrong. If you predict 300, that's a lot wrong. So they see that as not binary, it's shades of grey. There's uncertainty rather than black and white certainty. But really, predicting flow units, it's not black and white, because if the real answer is that it's flow unit 4, a reasonable model, if it might be wrong, but it's probably going to predict 3, the nearest one. It's not going to predict 1. That's more wrong. So either way round, there's uncertainty. For me, there's no right or wrong. Try it both ways around. The only thing I would say is that if you do it this way, if you build a predictive model for permeability, then how do you give that permeability to the reservoir engineer? What's he going to do with it in his model? He's only going to do some sort of HFU classification based on it anyway. So if you go with the recommended workflow, then probably the reservoir engineer is going to prefer that methodology anyway. Now, of course, you'd be in the sat height module. This can all be done multi-well. So the interactive log plot layer that I was using, that could be multi-well across a whole field. You might have different fault blocks in here, so you can group the wells so that you can interactively adjust the free water levels. It really helps to be able to look at it across a field-wide perspective. And at the end of the day, this is going to be an iterative process. Does that model saturation profile? Now, what I was doing was comparing it purely to the SW in the wells. Now, if it doesn't fit, of course, it might even be that your original log porosity might be where a source of an error, or the SW that you're comparing it to, that might be a source of error. How much uncertainty do we have in the saturation? Quite a lot, depending on exactly how complex the interpretation is. Don't forget that there are uncertainties, errors in the core data. Those measurements of porosity and permeability, they're not absolute. Again, the fitting functions. Try different functions. There's a whole host of different functions. Try different HFU or rock typing. And it is normal to have to make several passes, around this loop to try and get, the best result. And ultimately, at the end of the day, it's not really about getting the best fit to the log-derived SW. Really, it's about, does the dynamic model provide, a good match? I mean, and the really best way to QC that is via history match. So actually, using production history to actually, validate the model at the end of the day. Thank you.
Okay, thanks for that, Paul. Well, I hope you all enjoyed that demonstration. I think it really showed the power of having a workflow that integrates multiple advanced modules rather than just using each module in isolation. As I said at the beginning, some of you may already have these advanced modules, but if you don't and you would like to try using them, you can contact us on the digitalproducts@lr.org email address, and we can arrange an evaluation license for you. And if you have any more technical questions, again, you can contact us on the same email address, and we will get back to you with an answer very shortly. Okay, well, we'll leave it there for today. Thanks again for taking the time out to join us, and hopefully we'll see you at another webinar in the future. Okay, bye for now. Thank you.